Okay, the next item on the agenda is a presentation by CNSC staff on the evolution of nuclear technologies as outlined in CMD 14M8. And we have in attendance Mr. Soulard from Can-Do Energy Inc. And we have also the staff who will make the presentation. And we also have Mr. Lee from Can-Do Energy Online. Can you hear us?
Yes, I can hear you.
Okay, thank you. So I understand that Ms. Tadros will make the presentation.
That's correct, sir.
Please continue.
Thank you. So good afternoon, Mr. Chair, members of the Commission. My name is Heidi Tadros. I'm the Acting Director General of the Directorate of Regulatory Improvement and Major Projects Management. With me today are Doug Miller, Acting Director of the new Major Facilities Licensing Division, and Marcel DeVos of the same division. Behind us and supporting us are Jerry Frappier, Director General of Assessment and Analysis, and Robert Rorko, Director of Assessment Integration Division. The purpose of our presentation today is to provide information on 3 topics with evolving technologies as a common theme, and to answer any questions you might have. This slide identifies our proposed outline for the presentation today. You will note again that the presentation is composed of 3 parts. The first part provides an overview of evolving technologies. The second part focuses on small modular reactors, what they are and what this means to regulation. And finally, the last part provides an update on the CNSC's pre-licensing vendor design reviews. This last part is a follow-up to CMD 10M14 presented to you in 2010. As per the outline, we propose to take questions at the end of each part, as the presentation as a whole is quite lengthy, and the break is a natural transition from one part to the next. So with your permission, I'd like to pass the mic on to Doug, who will walk us through the first part.
Thank you very much, Ms. Tadros. For the record, my name is Doug Miller, and I represent the new Major Facilities Licensing Division. So in the first part of this presentation, I'd like to take the next half hour, it might be a little bit more than that, to explain how reactor technologies have evolved since their inception in the 1950s. We'll then bring some of this higher level information back into the Canadian context, not only in view of new build, but also in view of the existing Canadian fleet of nuclear plants. The last part of this will turn our attention to the future, to the types of reactors on the horizon, typically referred to as Generation 4 reactors. The first part of this trilogy serves to provide you with some information that will be useful in parts 2 and 3 of the presentation. So, you may have heard at times generations of technology. So for the first part of this presentation, I'd like to walk you through a story to clarify what generations 1, 2, 3, and 4 are and what they mean. Broadly speaking, generations is an industry term used to describe vintages of reactor technologies. We'll discuss each generation in turn and give you an idea of why it emerged and what informed its thinking at the time. As we go through the presentation, I'd like you to keep the following in mind. Reactors have been evolving over 60 years and will continue to evolve. Older generations designs still in operation have proved themselves to be safe, and they've been upgraded over time to safety levels comparable to those found in new build designs. The newer designs themselves integrate lessons learned from existing designs, whether they be safety or performance improvements. So, starting with the first nuclear power plant starting in the 1950s, these are commonly understood to be Generation 1 plants, so the early days. It was a period of experimentation with many different ways to achieve and control efficient chain reaction. Many were being designed to produce power, electricity, because of the large amount of energy contained in a very compact fuel. The early designs produced power on a small scale between 50 and 300 megawatts electrical. Proof of concept was the main goal, and economics was a secondary consideration. Research efforts focused on producing concepts that worked with the state of the art at the time, i.e. knowledge of materials. These first plants had inherent safety features, and they were being considered where possible for design. However, what you'll see when we come back to the Generation 4 discussion is that many concepts were ahead of their time and could not go forward because of materials limitations or lack of analytical tools. So there is a bit of a back to the future theme here. Most of the light water plants around the world can trace their ancestry back to the first US and French light water designs. So at the time, the development was based on domestic capabilities. So in the UK, there was the gas-cooled Magnox reactors. In Canada, they went towards the development of pressurized heavy water reactors with our abundant natural uranium in Canada. In the US, they focused on pressurized water reactors, both land and marine-based. Boiling water reactors were land-based, and the research continued into the 1980s on gas-cooled, liquid metal, and molten salt reactors. In the USSR, they focused on light water-cooled graphite moderator reactors, pressurized water reactors, marine-based, and liquid metal reactors. And there was also a boiling water reactor variant. These champions set the stage for evolving technologies in each country. So, just for illustration, there's a couple of first-generation designs in Canada. Was a nuclear power demonstration reactor up in Rolfton, and it operated from 1962 to 1987. It was a small reactor, 22 megawatts electric. But you can see there the traditional fuel channels and feeder pipes. Douglas Point was built just after that, operated from 1968 to 1984, and 10 times bigger, so a scale up, 220 megawatts electrical. And it's the forerunner of the current fleet of CANDU type reactors in India. Other reactors is the Calder Hall Magnox reactor in the UK, and decommissioning is in progress. It ran for quite a long time, 47 years. 4 units at 60 megawatts each, so they're relatively small by today's standards. And the drawing on the right is the early boiling water reactor, the Dresden reactor, and it's in a safe storage state. And it's the one of the first boiling water reactors. Safety was originally built into these designs. Safety features were being engineered into the designs, but operating experience was in its infancy around the world. You could say that over-engineering was common in the face of uncertainties. They knew the technology was a challenge, and they provided appropriate engineering. The early designs were also being informed by earliest incidents in prototypes such as NRX, where there was a loss of reactivity, fire at wind scale, and in SL1 in the US, an improper withdrawal of control rod. It was recognized that defense in depth was important, but it was an early concept, and it focused on layers of physical barriers to protect failures. Okay. Some of the first generation plants are indeed still in operation around the world. They're subject to the same safety scrutiny, including post-Fukushima, as any of the other operating plants in the global fleet. They need to continually demonstrate safety and adapt the design to changing conditions and safety requirements. And for example, there's Atucha 1 that was started in operation in 1974 and is still operating, and it's a pressurized heavy water reactor developed by Siemens. And we'll talk a little bit more about post-Fukushima improvements later. The message here is even the old plants have been updated and can still operate and meet modern day safety requirements. Moving along, then there was the initiative to commercialize nuclear power plants, and that's the 1960s to today. These are commonly understood to be the Generation 2 plants. So these are the larger plants, and it's the majority of the 300, 400 plus that are in operation around the world. So at the request of large utilities that existed at the time, power production economics became the major consideration for operation. Bigger is better, but it's lower electricity cost or electricity price. The champion designs that we talked about in each country were scaled up to produce power on a bigger scale and to take advantage of economies of scale for power production. The focus was on optimizing the first generation designs based on the lessons learned from operation of those facilities. Hence, i.e. in CANDUs with the separation of safety and process systems and two separate shutdown systems was recognized early in the early CANDU designs. There were stronger and lasting materials in the face of degradation factors, improving the fuel, better neutron economy, improvements to safety system reliability, improving operability and maintainability while reducing dose, and to continue to evolve defense in depth. Examples of these, of two CANDU plants are depicted here. On the left is the Point Lepreau generating station, and it's an example of a standalone CANDU 6, 635 megawatts. This design has also been successfully built and operated in China, Korea, Argentina, Romania. On the right is Darlington. It's an example of the multi-unit CANDU 900 series, and as you know, there are 3 4-unit stations operating at 2 sites in Ontario. So that's Darlington, Pickering, and Bruce. Despite architectural differences, these designs are descendants of the NPD and Douglas Point reactors and have incorporated decades of lessons learned. All Canadian power plants have evolved to have a safety comparable to the Generation 3 designs that we'll talk about in a little bit. And we'll come back to that illustration with some discussion on the CANDU fleet. This kind of evolution in designs has happened in other countries. Speaking of other countries, looking at other parts of the world, we have selected 2 plants out of the global fleet. The first example on the left is the Borcel plant in the Netherlands. It's the Netherlands' only large NPP and has been in service since 1973. What is worth noting that has been through a full periodic safety review has undergone significant upgrades that make it comparable to a Generation 3 plant. It is licensed to operate until 2033. In the second example on the right, we show the turbine hall for the 3 Mile Island Unit 1. TMI-1 is an example of applied lessons learned from the 3 Mile Island 2 unit next door, as well as the Chernobyl accident. It is also an example of the evolution of materials knowledge and maintenance optimization. There's been significant upgrades to the facility that has been performed near the end of its 40-year license term, and the unit was granted a license extension by the US NRC to operate to 2034. Okay. So now we come to near-term new reactor designs that have started in the 1990s. These are commonly understood to be Generation 3 plants. And there's 3 distinct types that are forming, which is the very large plants, that's 1,100 megawatts and higher. And the French EPR might be one of the largest at 1,650 megawatts for developed countries with bulk grids. So you need the grid capacity to handle such a large reactor. Medium-sized designs, 500 to 900 megawatt range, still have a place in countries that could not support the large designs. And discussions beginning on the designs to address smaller developing grids, 300 megawatts. So once again, there's a wide range of technologies. Okay. So the focus was on optimizing the second generation designs based on lessons learned from operation of Generation 1 and 2 reactors. The improvements made to existing plants are now being integrated into the basic design of new plants, i.e., as a couple of examples, containment venting and hydrogen mitigation. Practical elimination of severe accidents is a goal. The core damage frequency and large release frequency, which are design metrics, are set an order of magnitude lower than in the Generation 2 plants. And there's greater use of passive safety features, where you require no external power or even operator action to perform its mission to safely shut down the reactor and keep the fuel cool. And these Generation 3 plants are being built now. We'll come to that in a little bit. So examples of the Generation 3 CANDU reactors are shown here. There's the Enhanced CANDU 6 and the Advanced CANDU Reactor ACR 1000. The CNSC has completed full vendor design reviews on these two next-generation CANDU designs. Both of these designs were targeted to different types of markets, which I'm sure CANDU Energy could speak to. Both designs have different operational approaches to address their potential customer needs, and as a result, they apply different safety approaches based on their operational characteristics. In the end, both sets of approaches can result in same long-term operation. Speaking specifically to the Enhanced CANDU 6, it remains in the detailed design phase and represents the next step in CANDU 6 evolution. Upgrades were made to the existing fleet of CANDUs have been built into this design, while retaining many of the safety features of the existing design. Examples of this are heavier pressure tubes, thicker pressure tubes, modernized digital instrumentation and control, and updated reactor core control. To continue with the brief discussion of Generation 3 designs, a summary is presented here. So there's the EPR reactor that's being developed in France. It's a very large reactor and it's under construction in Finland, France, and China. The AP1000 and its cousin, the CAP1000 in China, is an 1100 megawatt reactor. It's under construction in the US and China. Russia has evolved their pressurized water reactor technology into the VVER 1200 and is under construction in Russia, India, China, and Bangladesh. Korea has taken their version of the PWR and is under construction in Korea and United Arab Emirates. And then there's the Advanced Boiling Water Reactor in Japan, is under construction in Taiwan. Okay. So that's a bit of an overview of Generation 1 through 3. And a theme in this that we're hoping to illustrate is that there's continuous improvement and learning from major accidents. So over the decades of plant operation, there's been continuous improvement in the safety of CANDU reactors. This is being achieved through licensees operating experience sharing programs and self-assessments, industry peer reviews, ongoing CNSC regulatory oversight, integrated safety reviews supporting facility return to service and life extension projects, and addressing lessons learned from major accidents. We'll touch on each of these in this next section. Now, in particular with regards to OPEX, the existing fleet around the world had been heavily affected by three major accidents, unfortunately, is TMI, Chernobyl, and Fukushima. 3 Mile Island in 1979 and Chernobyl in 1986 all but stopped new build dead in its tracks around the world and forced existing plants to reinforce key safety principles throughout their organizations. These principles continue to dominate the discussions today. These accidents introduced concepts such as safety goals, probabilistic safety analysis, periodic safety review, and also brought stronger discipline to the defense in depth approach. They resulted in a global discussion on new terminology called safety culture that is developed into a host of industry and regulatory concepts and tools used to this day. Human factors has become a major component of the safety discussion, affecting everything from control room and field design to training programs and fitness for duty considerations. Fukushima in 2011 showed the need to pay even more attention to extreme external events, the need to assume the worst will happen and discuss what mitigation measures are available or needed. Multiple unit sites need to consider simultaneous multiple unit accidents involving major fuel damage. The need to reinforce the existing practice of periodically and systematically reviewing the plant safety case while asking tough questions has become apparent. And through this, existing plants continue to evolve over their lifespan. Okay. There's continuous improvement, and a key part of this, as well as improvements in industry, is the evolving regulatory requirements and guidance. Since the onset of the Canadian nuclear research in the 1940s, the regulatory involvement and industry has evolved over time. In particular, with the CNSC regulatory framework, we focused on ensuring requirements and guidance take into account operating experience, ongoing research and development, industry best practices, and lessons learned from accidents. We try to ensure that they're as technology neutral as possible and are being developed to anticipate new technologies and approaches to the extent possible and can be applied in a risk-informed manner. The philosophy behind our regulatory requirements that high-level requirements are principles-based or performance-based, and they can apply to any technology, although currently written based on experience for water-cooled reactors. Lower-level requirements, such as the CSA standards that you've just heard about, lean towards water-cooled technologies but are useful in regulatory discussions around other technologies. However, it's important to note, the more novel the technology, the more the design will need to be proven through R&D efforts. That's a lead-in, just to keep it in mind for Generation 4 discussions. The requirements and guidance that we're talking about, as in our current regulatory framework, are not only used for new build, but also also used in assessments supporting facility refurbishment, where licensees analyze and address potential gaps between plants' existing status and modern requirements. Now, the licensees are doing their part. They have programs to conduct self-assessments and peer reviews, and share and review operational experience. And in fact, some of the incidents that we've talked about have led to development of organizations like the World Association of Nuclear Operators and the Institute of Nuclear Power Operators. And those organizations perform peer reviews of the licensees, where it's in some ways it's, would say, self-regulated, but there's certainly extensive peer pressure on the licensees to improve without having the regulator come in. It's a very effective process. Another aspect in Canada of continuous improvement is license renewals, where the licensees take stock of their past performance and look forward over their next operating cycle and beyond. As part of the license renewal process, the CNSC assesses licensee past performance in a systematic manner, evaluates their improvement plans over the proposed operating period, and also discusses implementation of new regulatory documents, industry codes, and standards. Through the work of the licensee and the CNSC, there is a comprehensive update of the licensing basis of the facility. So while the industry and the licensees are assessing their safety case and proposing improvements and making improvements, the CNSC has ongoing regulatory oversight to maintain an open dialogue with licensees. And as part of this, we have a comprehensive compliance program, which includes well-structured baseline compliance program of inspections and desktop reviews, on-site surveillance and monitoring, and requirements for regular reporting and event reporting. Taken together, this provides a very solid regulatory oversight regime, and that's complemented by a very healthy safety culture by the licensees and carrying out self-assessments and peer reviews. All this contributes towards continuous improvement. Continuous improvement in the CANDO fleet safety has also been driven through life extension projects. CNSC regulatory document RD360, life extension of nuclear power plants, sets requirements for life extension. The underlying principles of RD360 are, is the right work being done in view of the proposed extended operating life? And is that work being done properly? So the main tool that's used in RD360 to address those two questions, in particular, is the right work being done, is an integrated safety review, and that identifies the improvements to be made to resolve safety issues, to address gaps identified through the comparison of requirements in place at the time of plant construction with current requirements, assesses the adequacy of the arrangements that are in place to maintain plant safety for long-term operation. As a result, the ISR process can validate the existing plant safety features and programs and result in some changes to plant systems and programs to improve safety. So it's a systematic, comprehensive review. It's quite a large review, but it can be very effective in, indicating areas for improvement. Safety-related improvements planned and implemented for life extension are changes have been made to existing plant systems to supply water to support cooling of the fuel during events, such as in Bruce with the moderator makeup. Upgrades to containment filtered venting systems. Improvements to hydrogen mitigation, which is hydrogen recombiners. And also there's been improvements to severe accident management strategies, processes, and components. We've alluded to improvements from Fukushima lessons learned. And in particular, the Canadian industry has been very active in implementing the actions from the CNSC's post-Fukushima action plan. So the CNSC action plan addresses the requirements to be taken by licensees to handle severe accidents, has improved the capabilities to withstand prolonged loss of power and heat sinks, improved the response to containment challenges and performance. There's provision of additional emergency mitigating equipment and resources, and there's also automated real-time station boundary radiation monitoring systems. Taken together with the OPEX, sharing of information, lessons learned from accidents, our regulatory oversight, evolution of the regulatory framework, and lesson learned life extension programs, and activities such as the post-Fukushima safety improvements, Canadian power plants are comparable in safety to third-generation designs. It's been tremendous effort over the decades to improve safety, and you heard about one today with fire protection improvements at Pointe-le-Pro. That's one example of many. Now for something a little bit different. Now we'll turn our attention to long-term new reactor designs, some that are under development now. There are many vendor initiatives in progress around the world, but they all have the same goals. These are actually referred to as Generation 4 series plants, and their implementation horizon is longer than that for the Generation 3 plants. The goals for these Generation 4 reactors is improved safety and reliability, so a larger push for passive and inherent safety features wherever possible, eliminating reactor core damage, also where possible, and reducing or even eliminating the need for off-site emergency response. So in this case, if there's an issue with the reactor, it shuts down safely and stays shut down. For sustainability, it's to get more efficiency out of the fuel using alternative fuels such as thorium. They're looking at minimizing nuclear waste and reducing the long-term stewardship burden. There's also, of course, a focus on economics to have a life cycle cost advantage over other energy sources, and to have a level of financial risk comparable to other energy projects, so it might be simplifying the design. And also, of course, proliferation resistance and physical protection is to make that as safe as possible. What stands out, though, when you look at the Generation 4 technologies, this emerging technologies, is that this generation of reactors are proposed to operate under conditions quite different than those for the traditional water-cooled reactors. And we'll get into that in a minute. Really, as alluded to earlier, what's old is new again. The Generation 1 reactors, some of the initial experimentation looks very similar to what's being proposed today. All of them had some advantages over the existing designs, but at the time of development, they also had technological challenges. Advances in analysis methods and material sciences means that these designs are becoming more achievable now. What makes these designs different is that they propose different fuel types, whether liquid-based or pebble-based fuels, or even new fuel types like thorium. They also take advantage of different reactor configurations, such as graphite moderator or even no moderator at all in the case of a fast reactor. There are also different ways to cool the core. Instead of water, you can use liquid metals like sodium or lead, or even gases like helium, nitrogen, or carbon dioxide. What we would like you to take away from this is that each technology does have its challenges, and all innovative features need to be proven. Every one of these designs has to be well supported by an R&D program, and in many cases, although in many cases there is also a fair amount of operating experience with the early prototypes that they can build on. A specific initiative is the Generation 4 International Forum. It's one of the largest international government and research-based efforts in the world to address evolving technologies. The forum is composed of a number of IAEA member states who have selected 6 reactor technologies for long-term intensive R&D efforts. And the types of technologies are the gas-cooled fast reactor, a lead-cooled fast reactor, molten salt reactor, sodium-cooled fast reactor, supercritical water-cooled reactor, and also a very high-temperature reactor. All these efforts are contributing to a greater knowledge into materials behavior and degradation effects in more aggressive reactor environments. The next couple of slides provide a little bit of detailed information on the specific technologies, but they show the kinds of designs being proposed and the conditions that will likely exist for their operation. For example, with gas-cooled reactors, you are operating with helium at very high temperatures compared to what we are used to in conventional plants. On the other hand, with a lead-cooled reactor, coolant temperatures are also very high, but the coolant pressure is at atmospheric pressure instead of the 9 to 15 megapascal range of a water-cooled design. You may also note that very high temperature reactors can lend themselves to alternative uses such as hydrogen production. And also in the table, you can see that there's small reactors in the 20 to 180 megawatt range that's almost like a nuclear battery. What is also important to note that some of these designs are intended to be large, while some might be better suited as small plants. Mr. Marcel DeVos on my right here will discuss a bit more of this in part 2 on small modular reactors. As an example of the Generation 4 reactors, we present 3 different types of lead-cooled designs. It's being looked at closely by many countries right now because the design has a number of major advantages once you get past chemistry and erosion issues in the material. So if you can improve the materials, then the reactor is operable. Lead has a very high boiling point of 1745 degrees Celsius, so will remain liquid even if the fuel temperature gets high. This means that cooling will be maintained. The reactor can be run at higher temperatures. That means that plant efficiency will be higher and you get very high steam quality or heat that can be used for processes that conventional reactors cannot. As I mentioned earlier, these reactors run at atmospheric pressure, which means pressure-based accidents can be eliminated. If the pressure vessel does leak, the coolant will freeze and plug the leak. Lead does not react with air and does not help or interfere significantly with the reaction. But using lead coolant means you need the right materials and chemistry conditions in the core to protect against corrosion and flow-induced erosion. There are 3 designs being proposed for near-term construction. In Russia, there is the SVBR 100, which is a small modular reactor which will be the first of a kind for a future fleet. In Romania, there is an advanced lead-fast reactor European demonstrator, or the nice acronym ALFRED, which will be a prototype for larger production design. And in Belgium, there is the MIRA accelerator-driven research reactor, which is also a proof of concept design that will double as a research reactor. So there's an awful lot of innovation out there. So, in conclusion to part 1, safety is deeply rooted in the Canadian regulatory framework. Lessons learned are continually being implemented by industry. Reactors have been evolving for over 60 years now and will continue to evolve. Each generation has seen significant improvements in performance and safety over the previous generation. Older generation designs still in operation have been upgraded to safety levels comparable to those found in new build designs. The Canadian regulatory framework itself has evolved with the state of the art, and continuing efforts by the CNSC to keep the regulatory framework flexible and technology neutral is looking towards the future. And that concludes part one.
Let's move on to the second part, please.
Okay, good afternoon, Mr. President and members of the Commission. For the record, my name is Marcel DeVos, and I work for the new Major Facilities Licensing Division, and I'll spend the next 25 minutes or so to give Doug a break on his voice, focusing on small modular reactors, or SMRs, explaining what they are and what it means to regulation. So in this presentation, I'll cover the following topics. What exactly is a small modular reactor? If SMRs are deployed in Canada, where might they be and why? I'll speak briefly on the CNSC's readiness to regulate SMRs. I will discuss progress CNSC staff is making in characterizing and addressing regulatory policy and technical issues. And finally, I will discuss international activities currently in progress around SMRs. The concept of a small modular reactor is really just, again, a marketing term used around the world for a reactor facility intended to be smaller than a traditional nuclear power plant, or NPP. There are many different interpretations of the term SMR, and some countries actually include medium-sized reactors as well, and these could be in the range of around 800 megawatts electric, which is actually quite large, and would include the enhanced CANDU 6. So we know that they're being designed to produce electricity and or process heat, could be both. They most likely will be modular. That means that they'll be constructed of factory manufactured pieces which are integrated on site. This is actually a very common and old practice in both shipbuilding and the aerospace sectors. They might be water-cooled, but as we've learned earlier, they might not be. Vendors are also looking to target lower upfront capital costs to make them cheaper to construct upfront and make them more affordable in the long term than NPP designs. But I will stress they likely will be more expensive to operate on a day-to-day basis. They're not necessarily competing with nuclear power plant designs either, and I'll explain why later on. In Canada, all reactors are regulated within a continuum of requirements. SMR as a term actually has no regulatory meaning in Canada. As you can see from the diagram, some SMRs will be large enough that common sense should dictate that they really be viewed as small nuclear power plants, whereas others are small to the point that certain risks may be low enough for more use of risk-informed decision-making that might happen for larger units. So on the left-hand side of the diagram, we have the Babcock & Wilcox, or Generation M-Power design. It's an example of a small NPP, but it's labeled as a SMR. And on the far right-hand side is another design from Japan called the Toshiba 4S. It has two different versions, a 10 megawatt and a 50 megawatt electric version, and those are examples of a small reactor. In both cases are touted to be SMRs. As an example, in the diagram we've indicated two regulatory documents applicable to design specifically, namely RD 337, which is applicable to NPPs, and RD 367, which is applicable to small reactors. The two documents are actually very similar, and they show that there's really no special rules for small reactors. The approximate value of 200 megawatts thermal that divides a small reactor from an NPP was created to be a guideline only, and it's based on the premise that for smaller core inventories, some additional flexibility in the use of grading might be possible in certain cases. So RD 367 for the small reactors simply reflects where this additional flexibility in use of graded approach exists. So just for the note as well, RD 337 is actually being converted and republished as Reg Doc 2.5.2, and I believe you had that presented to you a number of months back. So it's important to understand that everything depends on the safety case put forward by a proponent. As Doug discussed in part one, many of the earlier reactor designs were in fact quite small and had a lot of fundamental attributes of an SMR, with only difference being that they were not designed to be constructed in modules or for fleet deployment. In this slide, I give you an example of a sodium-cooled fast reactor called EBR-2 that was run by Idaho National Labs. This particular reactor used metallic fuel versus the ceramic-based fuels that we're used to in our designs. It achieved first criticality in 1965, which meant it was designed in the 1950s and was capable of producing both heat and electricity on a small scale for the site that it was placed on. One key design goal for SMRs is to have a reactor core with inherent safety characteristics. What this means is that off-normal situations cause the reaction to shut down with no human intervention. EBR-2 actually demonstrated this type of behavior in 1986 when, under controlled experimental conditions, the shutdown systems were blocked and the reactor coolant pumps were shut down with the reactor running at full power. This demonstrated that with the loss of shutdown and loss of coolant circulation capability, the reactor power dropped to near zero in approximately 300 seconds. This particular reactor that's in this diagram is a forerunner of the GE Hitachi Nuclear Energy's 300 megawatt PRISM Generation 4 conceptual SMR design. So although this design was a success, the use of sodium coolant still presents some hazards that need to be mitigated, and all of the designers around the world are finding different ways to mitigate the sodium hazards, because exposure to air for sodium is explosion hazard. In this photo, you see the world's currently largest nuclear icebreaker, part of a lineage going back to the 1950s. It contains a marine-purposed SMR. This vessel is powered by two 171 megawatt thermal pressurized water reactors utilizing fuel enrichment in the range of 45 to 75%. What you might find amusing is that this particular vessel also doubles as a polar cruise ship with 64 first-class cabins and a heated indoor pool, among other luxuries. There's a much bigger icebreaker design under construction that will use different reactor design with low-enriched uranium fuel. In this photo is another example of a Russian SMR being loaded into the first of 7 planned floating nuclear power plants. The OKBM Afakantov, which is the first floating nuclear power plant, is designed to use two designs called KLT-40Ss. They're pressurized water reactors that will supply upwards of 70 megawatts electric to coastal locations with no access to a regional grid. In this case, however, the reactors are not used for propulsion of the vessel itself. The vessel is intended to be towed to where it's needed, and refueling is done on site. The center vessel in the contraption you see hanging from the rigging there is the reactor vessel itself, which would be replaced as an entire fuel cassette. So you don't replace individual elements, you remove the entire cassette from the vessel. The KLT-40S is the latest iteration of a reactor design that's been around for about 20 years in other Russian marine applications. We're aware that SMR vendors who are interested in Canada are seeking to address the needs of two distinct markets. In the far north, currently power is locally generated mostly by fossil sources, and the cost of power is very high. We may see very small SMRs in the range of 10 to 25 megawatts electric per unit proposed for resource projects, mines, northern communities, or even military use. In the south, however, we may see more traditional, what we would call normal-sized SMRs like the B&W npower I showed you earlier. I'll expand on these two markets in the following slides. It is important as a regulator to understand potential changes in the industry we regulate in order that we can be ready to address the questions and issues that come with these changes. In southern Canada, it's our understanding that in many provinces there's projected growth in industrial power demand, such as an increased interest in mining. There's a desire or mandate to gradually phase out coal generation. Grids are going through a renewal process at this point in time, and decisions need to be made on changes to grid architecture. Future facilities need to fit the capabilities of that architecture. They're looking at diversification of power sources as an overall goal to ensure a balanced power supply. And utilities are seeking the ability to export power between provinces and or with northern U.S. states. So in this slide, here's a list of reactor vendors who have indicated interest in exploring deployment in Canada. And I will point out that the Westinghouse design, which is second from last on the list, as of yesterday have decided not to pursue this market, as you're well aware. The state of development of these designs varies from conceptual designs to certified and ready-to-build designs. All of these designs range in power output from 100 to 300 megawatts electric, and they're all water-cooled. We would expect all of them to be licensed following the same approach that we would use for a normal nuclear power plant project. We cannot predict if all of these technologies will compete for projects, but based on what we learned from the new build NPP experience to date, we believe it's likely project proponents will want to take advantage of the pre-licensing vendor design review process to evaluate and shortlist technologies for consideration. And Mr. Miller will be speaking to the pre-licensing vendor design review process in the third part of this presentation. Here's one example of a pressurized water SMR. This is, again, the generation M-Power design, and its planned electrical output will be 180 megawatts electric per unit. In the middle of the slide is the integrated reactor vessel, and it will be located in a containment structure located either below ground, as indicated in this slide, or for other designs, it could be located above ground as well, in a more traditional containment vessel. What we mean by integrated reactor vessel is that the reactor core, reactivity control devices such as shutoff rods and drives, steam generators and pressurizers are all located in a single vessel. One of the main reasons being claimed for designing a reactor this way is to eliminate the possibility of a large loss of coolant accident, because you're eliminating all of the reactor coolant piping that you see in a traditional nuclear power plant design. The vendor's intent is also to be able to factory mass produce these vessels and transport them either by rail or road, either as an entire piece or in prepackaged sections for faster installation at the site. This is part of an aim to reduce construction costs and time at the site. So all of the designs I showed you on the previous slide use a variation of this integrated light water reactor concept. One question that likely emerges in your minds is what interesting regulatory issues might these designs bring to the table? Our understanding is that we need to be prepared for proponents to make proposals that take advantage of what these designs claim to offer, such as they're looking to have smaller emergency planning zones, claims of greater safety that preclude the risks of major releases. They're looking to have smaller plant staff complements, in other words, a smaller number of operating and maintenance staff. The idea here is that they're making claims of greater plant simplicity, coupled with increased use of automation, meaning that there's less staff needed to run and maintain the plant. It's important to note that in some cases maintenance approaches have not been fully developed yet, and that changes to some codes and standards may be needed, which speaks to some of the work that the CSA is doing, where we're asking industry to speak with them. They're looking to have reduced security staff, with a greater emphasis on plant design features to increase security, such as having the nuclear island located below ground where people can't get at it. Acceptance of proposals, of course, is highly dependent on the facility safety case, and we expect claims to be supported by evidence. All of these vendors are performing research and development activities in preparation to support future customers. A vendor design review would, if initiated, give us a good first indication of the strength of that R&D program. So let's shift our focus now to northern Canada, where we've been informed that the business drivers for utilities are quite different from what we've been hearing for more traditional southern-based utilities. In northern parts of most provinces, grid reliability and access is a very big issue. Upgrading and expanding the existing grid network is very expensive because this means hundreds of kilometers of power lines need to be added and maintained for customers who are very far apart from each other. Currently, major customers like mines increase reliability by using local fossil generating sets. But this means delivering and storing large amounts of perishable fuel, among other considerations. In the far north, there's no grid at all. All power is currently generated locally using small fossil fuel sets, and delivery and storage of fuel becomes even more of a challenge because the supply chain is easily interrupted by weather or refinery problems. So what this means is that the electricity generation can cost anywhere from $1 to $2 per kilowatt hour as opposed to the roughly 10 cents that we pay. CNSC has been contacted by 4 different vendors who are in the early stages of looking into how they might address this unique market. There are likely more vendors out there that we're not aware of yet. Most of these vendors have indicated to us that mines and communities do not have the capability, nor do they want to become the licensee. This means that a vendor, build, own, operate fleet model with long-term power contracts for customers may become the business and licensing model for these types of projects. The biggest design constraint in the north is imposing on designers of reactor technologies is that no refueling or storage of used fuel will be permitted on a site. This has apparently been driven by a lot of public input to the vendors. So listed here are some of the companies who have contacted the CNSC asking for information about licensing and pre-licensing technical discussions. I won't read the list, but I'd like to point out that all of these designs, with exception to one, are Generation 4 designs using enriched fuel and alternative core coolants. With exception to the Toshiba design, all vendors are looking at a vendor build, own, operate model, which means that they would be the licensee of not only the site, but also the factory that will mass produce the reactors and fuel them. To address the no refueling constraint I spoke to in the previous slide, one of the biggest differences between these designs and the larger ones I showed you is that the entire core assembly is designed to be factory fueled and shipped to the site for installation. At the end of the fuel cycle, which can range from 5 to 25 years, the intent is to load the used vessel into a large transport flask and ship it back to the factory of origin for refurbishment or decommissioning. That factory could be in Canada or it could be in another country. All of these vendors are exploring the pre-licensing vendor design review process as a planning tool for potential development. This slide is an example of one of these smaller SMRs, and it's actually a big one for a smaller one. This design is called the Gen 4 Energy Module from the US, and it's a lead bismuth eutectic design. At 25 megawatts electric or 70 megawatts thermal, it would be a large plant for this type of application, so it might be proposed for a large remote mine for electricity production and simultaneous process heat. And the red circle in the diagram indicates the actual nuclear island, which is actually quite small. And that has the replaceable reactor vessel in it. For these designs and licensing scenarios, the potential regulatory issues become more complex and will have a longer time horizon. Some of them will be public acceptance issues as well, regardless of whether it can be done safely or not. Proponents will be proposing concepts such as I spoke to earlier, transportable nuclear cores, very small on-site plant staff complement coupled with autonomous operation and remote monitoring or intervention. There are technology claims that preclude any risk of fuel melt or need for short-term response to events because of passive and inherent safety features in the design. They're looking to have potentially no on-site security staff at all. Vendors are designing plant features to take on the full role of on-site security through design features. In fact, in a remote region, they're questioning whether an on-site security force would actually be of any use at all. It's very important to note that in remote regions, emergency planning is more complex because the infrastructure may not be currently present. You can have significant delays in response due to weather, and the sites would be very far apart, meaning that response teams would have to carry emergency equipment with them and transport themselves to the sites on short notice. Vendors have indicated that most of these proposals would be rolled out over a very long period of time as part of the vendor R&D program. So for example, the first plant would not likely use a transportable core. We do note that further regulatory research is needed by CNSC to understand and regulate implications of these concepts. It's important to note to point out that industry is expected to lead the discussion on what precisely their regulatory and licensing issues are and how they might be resolved. Some of these issues, which I discussed a few slides back, will need time to resolve. CNSC's role is to clarify our requirements to facilitate that conversation. For example, how are they planning to prove some of the novel concepts that they're developing? How will the codes and standards be amended or created? What are some of the key public acceptance issues? Some broader issues will likely involve discussions before you, the Commission, such as the idea of transportable reactors. I'm sure will raise a lot of interest in the coming years after the steam generator issue. And there will be also a discussion on emergency planning in remote regions. CNSC is encouraging the SMR community to participate in public consultations on reg docs, as well as standards of the CSA, and to ask themselves, will the requirements and guidance work for SMRs? One issue that I introduced earlier is the idea of autonomous and remote operation of reactor facilities. So the idea here is to have a very small on-site plant complement, but you would be actually, the reactor itself would run by itself, would be fully automated, but the idea would be to be able to monitor it from a distance and intervene in operation as they see fit. So this approach might be used for very small SMRs in remote regions, but is not likely for larger designs. So we are aware that it's technologically possible to develop an automated facility based on what we've seen in other industries, But we have to better understand the state of the art and have it explained to us by industry why it's safe. Industry needs to examine public acceptability, which I would argue is the largest issue, to develop a position and plan to show how confidence will be developed. And do existing requirements, codes, and standards need to be reviewed for applicability in this case? So this is looking at instrumentation and control standards. So are there any additional human factors requirements or guidance needed? So just a few of the questions that we have. So looking at the Act, the regulations, and the licensing process, CNSC can conclude that the existing regulations under the Nuclear Safety and Control Act are already suitable for regulating activities involving SMRs. The licensing process is risk-informed and independent of reactor size. The license applications can be reviewed in series or in parallel, depending on the needs of the licensee and their readiness state. As Doug explained in Part 1, our regulatory approach in Canada means that an applicant can propose to address requirements in a risk-informed alternative manner. So in view of the potential challenges, if we look at the first group, these are water-cooled reactors. The SMRs would be the larger ones. The existing requirements and guidance apply in technical and licensing discussions. Most existing codes and standards are applicable, but some may need revision to reflect new and alternate methods being proposed by these technologies. And then if we look at the second group of reactors, the non-water-cooled or transportable SMRs, some new requirements and guidance are likely needed to supplement existing ones that we have in place. And many new codes and standards will need to be developed because of new approaches, technologies, and materials. A few years ago, we started looking into potential regulatory issues around SMRs by looking at what was going on in the United States. The US NRC produced a paper to their commission that spoke to the fundamental issues that SMRs brought to the table. For example, SMR owners would likely seek to operate their facilities with lower staff complements, but staffing numbers are actually written in law or rules in the US. From this report, we were able to show that a large number of US issues are not the same issues in Canada here because of our more flexible approach. A few issues raised by the NRC, however, will need to be looked into in a bit more detail by us. We're attempting to identify major issues roughly by safety and control areas for all SMR types, and we expect this will take about 8 months to a year to complete. The intent is to take a first cut at documenting issues and estimating the effort needed to resolve them. And the issues, of course, will be risk managed. So we're aware that some issues such as emergency planning will involve a very wide group of stakeholders at multiple government levels. On the global stage, there are a lot of industry-led efforts, such as by the World Nuclear Association, that are examining SMR licensing and safety issues. Regulators are starting to discuss organizing a common forum to discuss SMR regulatory policy and issues on a global scale. The IAEA is actually taking a first step with a consultancy in February of this year. It's actually this month. And this forum will involve the Multinational Design Evaluation Program, who's doing similar work on the nuclear power plants and has been operating for years now via the Nuclear Energy Agency. So CNSC will be participating in this forum in February. So to conclude Part 2, SMR should be thought of as just smaller reactors with different configurations. Some designs will have characteristics and deployment timelines of a Gen 3 design, and others will have characteristics of a Gen 4 design. The Canadian regulatory framework is flexible and technology neutral, but in some cases we still have to develop additional requirements and guidance for emerging technological approaches. We can already license SMR sites with existing processes. Industry is expected to lead the discussion, but CNSC staff are working to anticipate the regulatory questions that need to be resolved. And of course, the Commission will be kept apprised of ongoing efforts and consulted on key issues.
So I'd like to move on to the third part and then open it up for discussion.
Okay, thank you very much, Mr. President. It's Doug Miller for the record. So we've just gone through a discussion of the evolution of technologies and looking at small reactors. Now I'd like to talk about the pre-licensing vendor design review process and an update on an evolving tool. So in this, we'll give an overview of the pre-licensing process, an update on the status of completed reviews, some lessons learned from the pre-licensing vendor design review activities, and finally conclusions. Back a couple of years ago, staff gave an overview of the process. That was in the previous CMD 10-M14. And in that one, it talked about the objectives and review phases, benefits, technical review areas, review criteria, communication findings, and a little bit of discussion about the multinational design evaluation program. And we presented the status of reviews for 4 vendor design reviews ongoing. This presentation is an update to that one, plus additional thinking and new information. A vendor design review is a tool for reactor vendors, and it's to determine whether the vendor is ready for potential deployment in Canada. So often they will have an interested customer with them, but they are choosing to go through a vendor design review process. It's a proven and standardized process to evaluate in principle whether there are fundamental barriers to licensing the vendor's reactor design in Canada. The process should not be triggered unless the vendor's conceptual design is essentially complete and the basic engineering program has begun and design requirements are being established. The outcomes of the process helps the vendor have discussions with potential future licensees interested in their technology, and often there is an applicant in support of the project. A pre-licensing vendor design review, importantly, is not a licensing discussion. It's a technical conversation between the CNSC and the vendor. It's an optional process and not a prerequisite to licensing. A vendor design review enables vendors and utilities to communicate, identify, and address regulatory issues early enough so that delays in licensing and facility construction can be minimized. This can be a benefit to Canadians in terms of higher quality license applications, efficient and effective licensing processes, which means an overall cheaper project, and assists decision makers in quantifying project risks, informing costs and schedule estimates, and making the right decision, which ultimately, when it comes to electricity, is for the public. In this process, you have identified and resolved key issues before building, reducing costs and time risks, and ensuring public safety, that there's high confidence that regulatory requirements will be met. We'd also like to wish to emphasize what the reviews are not intended to do. They do not provide any assurances with respect to cost or schedule, economics, operability, maintainability, capacity factors, and they do not guarantee that the design changes may be required as a result of future findings. For example, during further, more detailed reviews under, say, a license to construct application or the results of commissioning. As we mentioned, it's an optional standardized technology neutral process. We use a managed process to evaluate in principle whether there are fundamental barriers to licensing the vendor's design in Canada, to ensure that the vendor receives a fair and consistent review, to standardize review topics and drive the review using a combination of documented internal work instructions and specialist expert judgment. But we also provide schedule flexibility within reason to take into account a vendor's design submission schedule. The outcome of the review process is not a detailed review of the entire design. It's a broad sample of key safety-related topics. And importantly, no approvals of designs or technical approaches are permitted. We will give an opinion, but it is not an approval. So they'll have a heads up of maybe these are some things that you need to work on or to address before you enter into an application review. The process is documented in regulatory document GD 385, the pre-licensing review of a vendor reactor design. And that was published in May 2012. The process preserves vendor proprietary information while giving the public information through an executive summary. The review is solely intended to provide early feedback on the acceptability of selected aspects of a nuclear power plant design based on Canadian regulatory requirements and expectations. It is certainly not a certification of the design and does not fetter the discretion of the Commission in the licensing process. It's understood by vendors that the CNSC will undertake a far more detailed review of the design at the review of a license application where the technology is targeted for a specific site. One of the lessons learned is that for the vendors not to come in too early. If the design is not complete, it's incomplete, partial documentation, we will give our opinion, and it will be maybe not a favorable opinion. It will indicate the status of the design and the status of the project. So if it's a heads up. Come with a suitably advanced design and ready for regulatory scrutiny. You may be wondering what the link is between the vendor design review and licensing. The results from a vendor design review process can be used to inform licensing activities. It can inform the license application and give a head start. It assumes that the vendor shares the results with the interested utility, and the utility can shape their own licensing submissions with the information obtained from the vendor design review process. And importantly, this information is part of the public process. The volume of information, the record is publicly available. Understanding the results of the vendor design review process can help a utility understand where project risks may emerge, and also to identify where the design may need adjustments to meet requirements, or where extra utility scrutiny is needed over the vendor so that the design is appropriate and meets requirements. There are other similar pre-licensing processes in other countries. So in Canada, we have our vendor design review process. It's non-binding, but can be used to inform licensing reviews. In the UK, they have a generic design assessment. It is binding and used in staff licensing reviews. In the US, there is pre-licensing discussions similar to the vendor design review, and then the certification process. The pre-licensing discussions are non-binding, but certification is binding. And a rule is actually written so that certification's in law. In Korea, there is a standard design approval process, and it's binding. And interestingly, in France, there's an opinion on the review of safety options, and that is non-binding and is used to inform staff licensing reviews. So what you see is that in some countries, there's a practice of early opinion, a heads up, are we on the right track? In other countries, when you enter into this, it's essentially part of the licensing process where it's an early review of the design. So, as you're aware, as we pointed out earlier in the first part, some of the new technologies such as EPR, AP1000, I'm throwing out a lot of acronyms, but newer pressurized water reactors and boiling water reactors are under construction in some countries. So a good question is, what happens if a design is already certified or reviewed in another country? The CNSC will not rubber stamp a design. The design must meet Canadian requirements. But we will go by the policy, the principle of trust but verify. We recognize that certification in another country is informed by that country's laws and regulatory requirements. However, other countries' requirements may be different than ours, and the differences need to be understood. So we will certainly consider other regulators' findings and conclusions, and will discuss with other regulators with them to understand the basis for their conclusions. And we'll illustrate that a little bit with the AP1000 review when we turn to the results of vendor design reviews. But it's really important to understand the similarities and differences in regulatory approaches between countries. And if they're similar, then you can spend less regulatory effort looking at those areas. But no, I don't think there's any two countries that have exactly the same regulatory framework and approach. Okay. So a vendor design review has 3 phases increasing in review depth. So there's a phase 1, which is approximately 5,000 hours of staff time. We can carry out this review in 1 year or less. The key objective is that does the vendor design intent show an understanding of Canadian requirements? We look at 19 technical areas. We call them focus areas. We'll describe those in a minute. And does the vendor understand regulatory language in Canada? From our reviews that we've performed for APMEA and AP1000, we found this was very interesting, that the Canadian framework is unique. It's not the US or any other country. There's specific requirements for Canada. It was very valuable to go through the Phase 1 review just to learn how to talk to each other. In a Phase 2 review, it's approximately 10,000 hours of staff time and can take up to 2 years to perform, and it can be done quicker. There's a Phase 1 follow-up and assessment of the design for fundamental barriers to licensing in the 19 areas. So in there, we do red flag if there are minor issues, areas for improvement, key issues where significant effort is needed, or a fundamental barrier to licensing. And the key issues are documented in our external summaries that are posted on our website. A key consideration is the vendor addressing Canadian design and safety analysis requirements for the design. So it's a real test of our regulatory framework and their understanding of Canadian requirements. Then after a Phase 2, the vendor may elect to go into a Phase 3 review where they will choose the topics and there'll be further discussion on regulatory issues. There's sometimes some difficult ones. We've got to the end of Phase 2, but the path forward is still needs to be worked on. So there's issues for resolution that are usually the focus of a Phase 3 review. You can stop between the phases, depending on whether you plan to proceed with a project or even deployment in Canada. You could go right from a Phase 1 into a licensing review, or you can choose to go into a licensing review after Phase 3. We do not put any restrictions on that. As we mentioned, there's a number of topics that we look at. So we have a standard set of 19 focus areas that are applied to any reactor technology. So we would apply these to the little 20 megawatt battery or to a 1600 megawatt plant. These topics are equally applied. It's a broad review to give an indication of how the vendor is addressing Canadian design and safety analysis requirements. The focus areas reflect topics that contain one or more of the following attributes. They span many technical areas, i.e. human factors engineering, have long lead times to develop and implement the programs. So for example, management system, especially in particular design management, where it will take time to understand the Canadian requirements and design governance processes, where changes to an approach by the vendor may require time before the vendor can proceed with the detailed design, so that might be related to instrumentation and control. There may be substantial R&D effort to demonstrate technology and methods, the use of novel features, or have been typically found to be problematic in past licensing discussions and from worldwide experience. Two good examples of that are safety classification methodology and instrumentation and control. I could read the 19 topics, but some key examples are defense in depth, classification of systems, structures and components, reactor core design, and emergency core cooling. Okay, so as we mentioned, we'd like to reinforce the process should not be triggered by a vendor unless the conceptual design is ready. The management system processes for the control of the design and safety analysis are in place. If you do not have that, then do not start a vendor design review, or else you may not like the report that you get. So we'll turn to the results of the vendor design reviews that we've done. So in the last year and a half, we were very busy. We finished a Phase 3 review of the Enhanced CANDU 6 reactor. It was completed in a year. We completed the review of a Phase 2 review of the AP1000 reactor, and that was completed in a little bit less than a year. Information from these reviews was used by the vendor companies to support their bid submissions to the Ontario government. In addition, We were also performing a phase 1 review of the ATMEA reactor. ATMEA's technology is the ATMEA 1. It's confusing, but ATMEA is the company, which is a joint venture between Areva and Mitsubishi Heavy Industries, and their technology is an ATMEA 1 reactor. And that started in July 2011 and finished in June 2013. And that's available for deployment in Canada. The results for all these reviews are available in the form of executive summaries posted on the CNSC website. So, Enhanced CANDO 6, we've carried out the 3 vendor design reviews. There's a conceptual drawing. I'm sure Mr. Soulard could tell us much more about it. So, the overall conclusion for the EC6 review is that CANDO Energy has taken the CNSC's regulatory requirements expectations into account, and there are no fundamental barriers to licensing the EC6 design in Canada. However, the key findings from Phase 3 are as follows: that the design provisions applicable for the generic design are already included or under development for the EC6 take into account the lessons learned from the Fukushima Daiichi accident. Regarding classification of system structures and components, progress has been made, but further discussions will be needed during the construction license application review. That there's some discussion to follow on the classification of key components. Additional work is needed by CANDO Energy to classify the exemption from the single failure criterion for the ECC, or Emergency Core Cooling System Heavy Water Check Valves. And there is also some debate on test pressures for containment leak rate testing. And finally, CANDO Energy has been, it's been highlighted that more detailed information is needed on radiation protection in design, and that would be looked at under a construction license. So of the review in Phase 3, those were the key findings and where there is additional work. Turning our attention to the AP1000 design, a Phase 1 review was completed in January 2010, and the Phase 3 was done in June 2013. The overall conclusion is that the AP1000 design provided a further level of assurance that Westinghouse has taken the CNSC's regulatory requirements and expectations into account, and that there are no fundamental barriers. These conclusions are subject to the resolution of key findings from the Phase 2 review regarding to the performance of the plant under beyond design basis accident conditions and severe accidents. There are some specific technical issues that need to be further discussed. There is more evaluation in the area of robustness and physical security. And lastly, is Westinghouse has committed to a design upgrade for the control systems and facilities to meet the requirements of RD 337 for the means of reactor shutdown. There is an agreed upon path forward in resolving these main technical issues. However, we'd like to illustrate the AP1000 review as an excellent initiative in international collaboration. To meet Government of Ontario bid timelines, the full review needed to be completed in 10 months rather than our normal 18 to 24 months. We used the following resources to inform the review activities for many of the Phase 2 topics. We held discussions with the US NRC, who had participated in the certification of the AP1000 design. This helps CNSC staff to identify areas where there was similarity or divergence of respective regulatory requirements. So understanding our framework, which I hope we do, but also understanding the US framework, we know what the differences and similarities are, and we knew where we could leverage the US NRC work, and that turned out to be very beneficial in saving time. We also looked at the results of the UK generic design review of the AP1000, and we know again where the similarities are between the US or between Canadian requirements and the UK, and we're able to leverage those results. And this work was done under MDEP using information in the MDEP library and through collaboration with both the UK and the US regulators, enabled us to carry out this review very quickly. We had tremendous support from the other regulators, and we're able to do a complex review in a short time. The ATMIA 1 review was completed in June 2013. And again, we found that the design intent was compliant with CNSC regulatory requirements and at the level of a phase 1 review meets the expectations for new nuclear power plant designs in Canada. The conclusion is subject to the successful completion of ATMIA's committed activities on the design, in particular those related to Canadian codes and standards. So that was an example where in the beginning of the project, ATMIA understood Canadian requirements, that we were not the same as US requirements. We have our unique requirements and framework. Key findings from the phase 1 review for ATMIA was, with regards to instrumentation and control, additional evidence needed to demonstrate the safety approaches for sharing of instrumentation between safety functions, sharing measurements between safety and control systems, and addressing common cause failures, and a little bit of work with regards to mitigation and prevention for mitigation of beyond design basis and severe accidents to show how the core catcher worked and whether or not they needed containment venting, and a small amount of work on out-of-core criticality. But those were the key findings from the ATMIA review. And we're in the home stretch. So, lessons learned from all of this work is that in phase 1, in particular, is very valuable for vendors to understand differences in the regulatory language from that of the vendor's country of origin. Each nation's regulatory perspectives, although informed by IAEA principles, are shaped by their laws, experience, and cultural attitudes and attributes. Vendors need to be prepared to take the time to understand and adapt the regulatory language used in the country of interest. And a vendor design review certainly helps to identify those issues and get on the same page. Secondly, we found there are differences in regulatory mandates. Different nations' regulators have different mandates. Some were surprised to see that we look at hazardous substances. We're much broader in our regulatory mandate than some other countries that solely focus on nuclear and radiological safety. So you have to consider nuclear safety, but not all conventional safety. Well, I just said that one. And that the differences in the mandate can have a fundamental effect on how regulatory requirements are expressed. So the vendors need to do some homework to understand the requirements of the regulator, of the CNSC, and shape their submissions. The vendor design review also helps us to understand the story behind the vendor's approach. For example, in some countries, safety classification is quite prescriptive, where in others, like Canada's, it's more of a performance-based approach, where you have to look at the safety function for that component and then sort out what its classification is. The CNSC will expect the licensees to understand the hows and whys behind the vendor's methodologies, because it is key to configuration management over the life of the facility. So there's much that we learned about dealing with the vendors, and much that the vendors learned about Canada. Okay. What we also learned and discovered, and we're very encouraged by, that the CNSC requirements are indeed flexible and technology neutral. Both the ATMIA 1 and AP 1000 reviews showed that Canadian requirements are technology neutral and applicable to non-CANDO designs. Requirements were applied to new passive features, new designs of coolant pumps, and different approaches for instrumentation and control. The feedback from these discussions during these reviews was used in the updates to Reg Docs, for example, on design, Reg Doc 2.5.2. So it was a very good way to test the interpretation of requirements in guidance language. Okay. Pre-licensing reviews are gaining importance worldwide in light of new technologies. Designers are seeking ways to make designs acceptable in many countries and standardizing. Utilities and governments are seeking to reduce project risk by seeking early opinion of the regulator on how well a design would meet a national requirement. And the pre-licensing reviews permit international regulatory forums such as MDEP to compare notes and even work to harmonize regulatory approaches. So, in conclusion to part 3, The optional pre-licensing vendor design process has been shown to be a useful risk reduction tool. It reinforces Canadian regulatory requirements and CNSC expectations with vendors, so they know who they're dealing with and what our approaches and attitudes are. It's a predictable and fair process to look at how a design will meet Canadian requirements, so we ensured there was a level playing field with doing the vendor design reviews. The same criteria was applied for all. And it also confirms the vendor is actively seeking the resolution of design issues identified, and it can inform the licensing process. And that's it for part 3.